Welcome to this next video in Mathematics 1. Today we're going to talk about Tableau Form and Echelon Form for systems of linear equations. So today's section is called SLE, Tableau Form, and Echelon Form. So the idea of Tableau Form, that's the first thing we're going to talk about. The idea of this Tableau Form is basically to simplify notation just a little by concentrating on only the real data. So basically, we're leaving out the plus or minus signs, and we're also leaving out the variables. Just concentrate on the coefficients and the right-hand sides as the data that actually defines a system of linear equations. So the idea is that we want, for simplicity, a nice and compact representation. Simplicity, we want a compact representation of an SLE. Does not contain any unnecessary information, and that makes it easier to do computations, to do the manipulations that will be required later on for the solution of a system of linear equations. And this is the idea of Tableau Form. Here's our definition. Let's say we have a system of linear equations. So let a system of linear equations with m equations and n variables be given through coefficients, all these alpha ij in R. I goes from 1 to m, and j goes from 1 to n. And we also need the right-hand side. We call those beta I from 1 to m. So those are the values that actually define the system of linear equations. Let me just write this in a compact form, and that is what we call Tableau Form. The Tableau Form of the SLE is then given by the following representation. What we do is basically we take the coefficients and we write just the coefficients. So we write alpha 1, 1, alpha 1, 2, alpha 1, 3, and so on the first line of that tableau. We write the alpha 2s on the second line of the tableau, and so on. We do this for all the rows. So we just do away with the x's, with the variables, and we do away with the plus signs between those, because we know those are going to be there, so we know what this notation means. And we just write down the coefficients that define what the system actually does. Like this here. And then the right-hand side, and that right-hand side is signified by a vertical bar. So that is meant to divide that tableau into two parts, the coefficients and the right-hand side. Okay, so this is the Tableau form. And for a homogeneous system, meaning all the betas are 0, the right part of the tableau may be omitted. Means for a homogeneous system, the tableau would then look like this. Just the alphas. And no right-hand side. Yeah, so that implies the right-hand side is 0. And that is a very, very concise form of writing down the system of linear equations. And it's also a form that is suitable for manipulations. If you want to do computations, you can do that very nicely using this form. But before we get to that, let's first have a look at a very special case where the solution of a system of linear equations is particularly easy to determine. And that is the so-called echelon or staircase form. So for the solution of a system of linear equations, a particularly easy case is a system in staircase form. Like this. What I mean by staircase form is a system that looks like the following. We have a 1 in the upper left corner. Zeros below that. I just do a 3 by 3 system as an example. We'll generalize that later on. Then again, we have a 1 here, a 0 below that, and a 1 here. And we have some coefficients on top of those 1 entries. So we have the coefficients here, alpha 1, 2, alpha 1, 3, arbitrary coefficients, alpha 2, 3 here, and of course the right-hand side. Now, if we have a system like this, the solution can be easily determined. And it can be determined by a process known as back substitution. We've seen this already in the context of our examples. So the idea is to solve the system backwards. Again, notice we have this staircase form here. So here's the staircase. And you'll notice we'll have these 1s here, standing right on the stairs. So the idea of this back substitution is to start from the very last row and the very last column. So you start in the 3rd row, in this case. And the equation that is in the 3rd row, that's encoded in this tableau, well, what does that basically say? We have 3 columns. So let's say each column corresponds to a variable. So let's call these x1, 2x3. Those are the columns. So that last row corresponds to the equation 1 times x3 equals beta 3. Well, that's easy to solve. The solution is actually right there. x3 is beta 3, right? So we have x3 already. And once we have x3, we go back. We go to the second row. The equation encoded in the second row, that is 1 times x2 plus alpha 23 x3 equals beta 2. Now that is easy to solve for x2. So we have beta 2 minus alpha 23 x3. We know x3 already. Just take this value, substitute it for x3 here, and then compute the solution. And there we have x2. And finally, for the first row, that one, here, this first row, the equation that this encodes is 1 times x1 plus alpha 1, 2 x2 plus alpha 1, 3 x3 is beta 1. And again, that's easily solved for x1. x1 is beta 1 minus alpha 1, 2 x2 minus alpha 1, 3 x3. We do know x3, so we can just substitute that here. And we also know x2, so we can substitute that here. And that means we can compute the solution for x1. So using this staircase form, we can work our way backwards. And the important thing about this is that each equation only contains variables up to this element here on the staircase, right? No other variables than x3 in here. Here we have x2 and variables to the right, so x3 is also contained, but no x1. And here we have x1 and variables to the right, x2 and x3, which we already know by working our way backwards. So this is a particularly easy case. And that means that's the case that we would want for a solution, right? So this staircase form is something that is very nice if we want to solve a system of linear equations. So we first define what this staircase form, formally it's called Echelon Form, what this actually is for larger systems. We'll see one more example, and then we'll have a look at how to get a given system into this staircase form. What do we have to do to achieve this staircase form to then compute the solution? So let's formally define staircase or Echelon form. A system of linear equations is said to be in called either staircase form or row echelon form. From now on, we'll use the term echelon form. If its Tableau representation has the following property. So here's the properties we need. First, all 0 rows are completely at the bottom of the tableau. So every row that has only zeros in the coefficient part or even on the right-hand side is at the bottom of that tableau. We didn't have that in the example before, but we'll see examples with 0 rows in a minute. So all 0 rows are at the bottom of the tableau. Second property, For each row, we want that all the entries beneath that leftmost non-zero entry are 0. So here's the leftmost non-zero entry of row 2. All entries below that need to be 0. Here's the leftmost non-zero entry of row 1. All entries below that need to be 0. That's staircase form that we want. Okay, so for each row, all entries below the leftmost non-zero entry of the row are 0. And this leftmost non-zero entry of the row, that is called the pivot element. Leftmost non-zero entry of each row, if it exists. Of course, it doesn't exist for all 0 rows, is called pivot element. Third property, each pivot element is strictly to the right of all pivot elements in the rows above. Here, if we're looking at a pivot element like this one here, that is strictly to the right of all pivot elements of the rows above. So here's one row above, here's the pivot of that, and it is strictly to the right. And the next one is strictly to the right. Yeah, so we only move to the right as we move downwards for the pivot elements. Each pivot element lies strictly to the right of all pivot elements in the rows above. So that defines what we call echelon form. You will probably have noticed that I have not required the pivot elements to be 1 as they were in the example here. We had 1s in here. That's not strictly necessary. If you don't have that, then in this step here, and in this step, and in this step, you will have to do one more division. You will have to divide by that pivot element, right? It's not 0, so you can divide by that element. You have to do that additional step if it's not 1 already. We'll extend the definition a little to include that case as well. If we have those 1s, and if in addition to that, each column does not only have 0s below the pivot, but also above the pivot, and we will see that how we can achieve that. That would be called reduced row echelon. That makes things even easier. So furthermore, the SLE is said to be in reduced row echelon form, or just reduced echelon form. If it is in echelon form, and the following additional property called, and that is number 4. Every pivot element is a 1. And number 5, each column that contains a pivot element has 0 entries in all the other rows. Notice there may be columns that do not have a pivot element. We did not exclude that possibility. We didn't exclude that before either. There may be columns without a pivot element, but those do not necessarily have 0 entries in all the other rows, or no other rows, formally speaking. But if there is a pivot element, then there's 0 everywhere else in that column. So each column containing a pivot element has 0 entries in all other rows of that column. And finally, a column that contains a pivot element is also called a pivot column. So let's see a quick example of how that can look like, just so you get a feel of what Echelon Form means. Let's say we have a matrix that looks like this. I'll write that down, and then we'll see why this is in Echelon Form. There's a 1, and then zeros. There's a 0, a 2, and then some zeros. We have 0, 1, 0, 0, 0. We have 2, 1, minus 1, zeros. And then we'll have a right-hand side as well. Say it looks like this here. Okay, so this is a tableau for a system of linear equations. And let's have a look at the properties that we need. All 0 rows are at the bottom of the tableau. Here we have 0 rows, right? So property 1 is fulfilled. You notice there's one non-zero right-hand side, so that rule refers to 0 rows in the coefficients actually, right? Those need to be at the bottom of each row, disregarding the right-hand side. Then what else do we need? Well, we need for each 0 row, all entries below the leftmost non-zero entry are 0. Have a look at the leftmost non-zero entry. So here's one. Here's that for row 2. Here's that for row 3. And the other rows don't have a leftmost non-zero entry. So those here are the pivot elements. And you'll notice that we have zeros here. We have zeros here. And we have zeros here. Right? So that is rule 2, sorry. And finally, the pivots move from left to right as we go down the rows. So here's the leftmost pivot in row 1. In row 2, the pivot is directly to the right of that. In row 3, the pivot is strictly to the right. Okay, so we're moving right here. And this is our rule 3. Okay, so this matrix, this tableau here, this is indeed a tableau in Echelon Form. It does, however, not have reduced row Echelon Form. And easily see that because there's 2 here as a pivot for it. Yeah, and also above this pivot here, there's entries that are not 0. This is not reduced, but it is in Echelon Form. Okay, let's have a look at one that is also in reduced row Echelon Form. Simplify this one a little. 4 rows. This and we also get side. Right, and you can see again we have pivot elements here. Here's one, and the leftmost entry in row 3 is this one. So those are the pivots. Those are now all 1. All right, so that satisfies rule number 4. Again, the 0 rows are at the bottom. That satisfies rule number 1. We have zeros below the pivot elements. Here, here, and here. That satisfies rule number 2. We're moving to the right, strictly to the right. That satisfies our rule 3. And we have one more rule left, that's rule number 5. We need zeros above the pivot elements as well. So here's a pivot with elements above. Here's another pivot with elements above the first one. This one doesn't have any elements above it. So these 2 here are necessary for number 5. Okay, so this tableau here is in reduced Echelon Form. Now we know how to recognize a tableau in Echelon Form and what to do with it, namely solve an SLE by backward substitution. The next logical question is, of course, how do we transform a given tableau into row Echelon Form, not changing the solution space of the associated system of linear equations in that process? Is there a possibility to do that? And of course, that is the case. Otherwise, all this would be pretty pointless. And we talk about that in one of the upcoming videos when we talk about Gaussian elimination. I'll see you then.